Okay, morning, let's start lecture. So in last lecture we introduced a new concept called Laplace Transform, and the definition basically, given a causal function f of t, and we're going to do a integral type of a transform. So the way to transform that is just through this integral here, and so your time function t becomes an s function f at here, and s is a complex number. Okay, yeah. So this is a Laplace transform, and I showed you some common typical functions Laplace transform, which is the table giving it here. Okay, so a lot of useful ones, for example, the exponential one, the sinusoidal, okay, and a combination of exponential and sinusoidal. Okay, so those are very common ones here. So this is going to be there's formula sheet. You're going to have this. You can have this one in the final exam. So also the delta function, the unit step function, right? Okay. We also showed you some properties of a Laplace transform. Okay, so Laplace transform basically is a linear operator. Okay, a couple of very useful ones here is these two. So what's the Laplace transform of a derivative first order and second order? So since we're dealing with basically the highest order, we're dealing with the second order in this course, and this one and this one is probably gonna you have to memorize that. Okay, and you will have the formula, but I suggest you memorize this by heart. What are the transformation of these two at here? Okay. So there's another one here. It's also useful. This one, Laplace transform. Okay, f of t minus a, u of t minus a. So basically, you have a shifting of this original causal function. Okay, and the resulted one is basically e to the power negative as. Okay, f of s. And one of the assignments I think I'm going to give you is sort of a practice of this property right here. Okay, so that's the proof. A couple of these properties. One more I think I want to mention is this one here. Okay, so this is going to be used for one of the assignments too. So it's the Laplace transform of the integral of this function f. Okay, so you're integrating this function f here. Then the Laplace transform this one here, and it's capital F of s over s. Okay, over s here. Now, maybe I should write this this one down here and here. Okay, so this equal to s 0. Okay. So now if you compare these two properties here, okay, yeah. So look at what this s that here is doing, okay, associated with the type of function that you're transforming it here. So this is a derivative, and this is the integral here. When you transform an integral, and you have this 1 over s showing up at here. When you're transforming a derivative at here, you have what? S showing up here, right? So suppose you have an initial condition f of 0 is 0, so then basically this is just sfs right here, right? So essentially what happens here is this s itself, okay, is functioning as if it's a what? A derivative. Okay? And this 1 over s itself is functioning as if it's an integral here. Okay? Yeah. So and we're going to use this Laplace transform to solve. We'll have a better sense of this s and 1 over s here. All right? Yeah. So the other property I think I also want to mention is this initial value and the final value property. So initial value and the final value theorem. So we call it theorem. So basically, initial value, if you have f of t here, right? If you have time function f of t, so the question here is, what is f of 0 and what is f of infinite? Okay, so this is basically called initial value, and this is what we call f final value. Okay, so at time equals infinite, right, what's the value here? At time equals 0, what's that? Okay, so this is kind of useful concept because this f of t may be represented as the output of the system. Then people probably ask is, what happened when the system, or basically where will it settle down? Right? Is it going to settle down at 2 or 3, or maybe it's not going to settle down? Maybe it's just going to oscillate, or maybe it's just going to go crazy, right? So that's basically the final value meaning of this f of t here. Okay? Now, technically, you can see, okay, I'm going to just basically look at this f of t value at a very far away location t, and maybe at t equal to 0, right? But sometimes it's hard to do that. So the other way of doing this one here is using this initial value, final value theorem, which is a derivation from the Laplace transform here. Okay, and what it says here is, instead of looking at this f of 0 in the time domain, you look at this f of 0 using this Laplace transform. So it's s go to infinite, s capital F of s. So that's initial value here. And f of infinite, okay, is the limit s go to 0, okay, and s f of s. Okay. Yeah. So there's a proof in my lecture notes, so you can take a look at that. Okay. But the application of this one is very simple. So for example, right, let's say I have a maybe I already have this Laplace transform now. Let's say I have Laplace transform, which is s plus 2 over s plus 2 squared plus 10 to the power 2. Okay. So this is a Laplace transform, okay, and this is actually Laplace transform corresponding to f of t equal e to the power negative 2t and cosine 10t. Okay, this corresponds to this one here. So maybe let's just quickly verify if is it the Laplace transform this time function, this one here. Just go to your table, okay, and use this one in here. So as you can see, omega, right, in this particular case it's 10, and a at here is 2. So if you plug in this formula here, okay, so that's the Laplace transform here, right? Yeah. Okay. Now the question is, if I'm interested in f of 0, of course you can stop the 0t equal to 0 here, you get f of 0, right? But if I do it using this initial value theorem in here, then it's limit, okay, s go to infinite, okay, so s multiplied by this whole chunk, okay, yeah. So there is s squared at the top, but there's another s squared at the bottom here, right? So what you can do is you can do this, you can expand the top and the bottom. So s, when you expand it, the top is this, and the bottom is, okay, the bottom is this. Okay, just expand them out. Then you divide both the numerator and the denominator by s squared. Okay, so you can divide both the numerator and the denominator by s squared. Okay. Then this s squared cancel that. It will basically be 1 plus, right? So which is 1 plus 2 over s. Bottom here is 1 plus 4 over s plus 1 over 4 over s squared. So s is going to infinite. So this is 0, this is 0, this is 0. So overall this is what? 1. Yeah. So the initial value is 1. Yeah. Because I can, so then I can take this limit now, right? If I divide it by something else, it won't be that. here. Oh, that's the theorem. There's S here. Yeah. Okay. So similarly, if you plug t equal to 0 here, you get a 1 here, right? Yeah. So similarly, you can check this infinite. So what would be the infinite? F infinite, so you look at this, it should be, huh? You don't know? Why not? If you plug in t equal to infinite here, you should get what? 0, right? Yeah. So, sorry, what was it? No. Yeah, sorry. When you check infinite is for for t is equal to infinite, right? But for the s term here, you plug s equal to 0 here. Basically, same expression. See, right? Same expression here. Same expression, but you plug the s equal to 0. Maybe I'll just do it here. F infinite is the limit s go to 0, and s plus 2 square plus 10 square. So when you plug x equal to 0 here, this is easy. Just let x equal to 0. So apparently, this whole term is 0 here, right? Okay. So this is basically another way of finding the initial value and final value. Particularly in control system, many times in control system you have your model, and then you will have later we'll learn that you will have a so-called transfer function. Then based on the transfer function, okay, and you can easily verify what's your initial value or the final value. So you can know that whether you have a stable system or not. Okay, so the final value is a lot of times the most important part. Okay, any questions? Sorry, louder. L'Hopital rule? This one here? No, we didn't. Oh, can you use the L'Hopital rule? This one, no, you don't need to, right? L'Hopital rule is when the numerator denominator both go to 0, then you use the L'Hopital rule. But in this case here, when you ask this, both of this numerator and denominator go to the infinite, right? So you don't use L'Hopital rule. Here, when you let s equal to 0 here, the top will go to 0, but the bottom will not go to 0 here. So you don't need to use the L'Hopital rule here. Okay? Yeah. Okay, so those are the properties and the typical Laplace transforms. Okay, so the focus actually now is on the so-called application of Laplace transform. There are many applications of Laplace transform, but I'm going to show you two in this course. Number one is applying Laplace transform to convolution. So we spent a couple of lectures on convolution, and we focused on this approach called graphic approach, right, to solve a convolution in terms of convoluting two piecewise functions. Now this is a third approach, basically, the third one. The second approach, which is to use this Laplace transform. Okay. So first of all, the relationship between Laplace transform and convolution is this. Consider two causal function. Let's say f of t and the g of t. Okay. Then there is a corresponding Laplace transform, okay, for each one of them. So usually the convention is you use a small letter for the time function, you use a capital letter here, the corresponding capital letter for this Laplace transform, right? Then Laplace transform of the convolution, okay? So Laplace transform the convolution of these two time function is capital F of s multiplied by g of s. So here is basically the theorem here. And then again, I'm going to skip the proof. Okay, so there is a pretty lengthy proof in the lecture notes, which usually will bore people out. So you can take a look at this yourself. Okay, yeah. But this is actually a very elegant expression right here. So I think I mentioned this a couple of times. Basically, it's an idea of looking at the things from different perspective. So, for example, remember one of the simple case I was talking about is when we learn a complex number. So one way is we said we write the complex number into this kind of format here, right? Then when you have two complex numbers dividing by each other, okay, instead of calculating using this, say for example, instead of calculating using a1 plus jb1, a2 plus jb2, so you can use this r1 ej theta 1 and r2 ej theta 2 to do the calculation. And when you do this calculation, you're not doing division, multiplication. Then what happens here is this is just ej theta 1 minus theta 2. This is subtraction here, right? So same thing, if you have a ln, AB, so this is equal to ln A plus ln B. So this is addition. So you're getting away from multiplication A and B here. So this is basically a different perspective here. Same thing. Now you're not doing convolution. You're doing what? Here is you're doing multiplication in here, right? And of course, in the end, you're going to have to transform this back to the time domain, of course, right? Yeah. But however, doing this multiplication, I think, is much easier than do this integrals and graphical things here. Okay, so we're going to basically I'll show you how to apply this to to a simple example here. Okay, so here's the example. F of t is 4e to the power negative t u of t, and g of t is 5e negative 2t u of t. Okay, and let's try to find the convolution between these two. Okay. So this is more of like a midterm question here, which is a little bit simpler. But if I change this u of t to a box, right, of u of t minus 1, so that is basically much like the midterm question now, right? So a typical graphical approach is you're going to have to draw these two out, okay? Then you flip one and shift, and find overlapping, then you do the integrals here, right? Yeah. So now what we're going to do is we're going to use mixed theory here. So number one step, so we're going to basically calculate the Laplace transform this and the Laplace transform this, okay? So apparently this is very easy. Laplace transform f of t, this is 4e to the power negative t u of t. So which one is that? So this one here, okay? Yeah. So now I probably say, where's the u of t? Remember what I said about this table, right? This table basically I get rid of the u of t. Everything is a causal function at here, okay? Yeah. So looking at this one here, this is a 4 over s plus 1. Okay, so this is e to the power of negative t. That's this one. Then g of s, this is 5. So 5, okay, 1 over s plus 2. Okay. So that's Laplace transform these two functions. Okay, so now if I look at this theory here, the convolution of this basically is the inverse Laplace of this one here, right? So maybe I'll just write it down slightly here. So the convolution is basically the inverse Laplace of this f of s and g of s. Okay. So let's calculate this f of s multiplied by g of s, and then calculate the inverse Laplace. All right. So f of t convoluting g of t equal inverse Laplace f of s multiplied by g of s. Okay, yeah. We already have f of s, g of s now, so just multiply, just put them into together. Okay, so that's really nothing tricky here, just plugging everything into this formula. Okay, so now the next step needs a little bit skill now, okay, and which is actually what we're going to practice. So to find the inverse Laplace transform, now if you recall, you have basically one very traditional approach, which is to use the definition. There is this complex integral calculus that needs to be solved, right? Remember the definition. But that's not what we're going to do. And if you recall that, I said to find the inverse, we still use a table. So we try to find the s set here and then find the associated time function. Okay? Yeah. But for this particular case, what's the s? This is a 20 over s plus 1, s plus 2, right? But if you look at it here, I guess there is nothing like that here. Okay? Yeah. Now, what's given in this table here, what we call is it's called the simplest Laplace transform that you could have. Okay. So then the next step right here is, before you use the table, we're going to have to break it down into a simplest form. Okay. So break this into the simplest form. So how do we break it? Is this. So here you have two factors multiply each other here. Okay. And this is actually a technique that you should have learned in doing integral. This is called partial fraction expansion. So you separate this one here into two terms. So one term is, let's say, a over s plus 1. The other term is b over s plus 2. Okay. So you break it down into two terms like this. The reason is, the reason you can do that, okay, first of all, okay, if you put these two back into that format, right, you can see the denominator is still s plus 1 multiplied by s plus 2, right? Yeah. And the only question is, you need to find a proper a and b such that it give you back this 20 at here. Okay, so that's basically the purpose. So how do we find a and b? Well, I'll show you later. Okay, we have a formula doing that, but there are different ways. But in time for the right now, so let me just tell you what the a and b here is. There actually one is 20 at here, and one is negative 20 at here. Okay. So if you kind of doubtful it here, just put them back into this format, okay, and you'll see that you'll get exactly 20 over here. Okay. Yeah. So just remember, this technique here needs a little bit of further steps here. Okay, but we're gonna learn it soon. Okay, so now this is what we call the simplest form. Simplest form. Why is it simplest? Because you can't break it down to even simpler form anymore, right? And what's more, the inverse Laplace, basically the inverse Laplace over 20 over this minus inverse Laplace 20 over this. And this is essentially because the operator is linear, so you can use that linear property to break it down into separate parts. Okay. Yeah. So now if I look at, and I can take the 20 out of it. So now if you look at your table, the handout that you have there, so apparently, what is the inverse Laplace of the first one? Yeah. The second one? Exactly. Right, exactly. Okay? Yeah. So technically speaking, there should be a basically u of t multiplied here, right? Yeah. Because we're all dealing with the causal function, so then the convolution should end up with still causal things. So if you don't have a u of t here, usually I won't be too picky if I don't say this in the final exam, but you should understand that there is a u of t actually at here, right? Yeah. Is that good? Yeah. So this is, you look at this approach here, I think it is much easier to do than the graphic approach at here, right? Yeah. But in the final exam, you got to watch the question whether I'm asking you to use a Laplace transform or to use graphic approach though. Okay. Yeah. Laplace transform cannot be used on all the situation, because some time function, when you take Laplace transform, it's very hard to find. Okay. Because you look at the table here, those are basically some beautiful functions here, right? But if a very weird type of function, time function, and you might not be able to find the Laplace transform easily. So you still have to use the graphic approach though. Okay? Yeah. So I think I'm going to skip going to skip this example here. So let's take a look at the second type of application. The second type of application is, which is actually one of the focus here. It's the application of Laplace transform on solving differential equation. So the approach showing it here pretty much actually can be applied, not just restricted to the second order. It can be applied to higher order, which actually has more advantage here using Laplace transform of solving higher order differential equation. So I'm going to give you a sort of overall idea first, then we're going to go into look at the different cases. Okay, so we do have different cases here, and here's an example. So let's say I have a second order differential equation. I'm not specifying this f of t at here, so just sort of there's some input here, right? Now, if f of t is sine or exponential, then you can use the lucky guess, the method of undetermined coefficients. If f of t is nothing like that, you can use these variation parameters, right? Yeah. But now I'm going to use Laplace transform. So to use Laplace transform, the steps that you do is basically the first step is always what you do is taking Laplace transform of both sides of this equation. Okay, so taking Laplace transform of both sides. So this is transform, right? Basically, we're not going to stick with the time domain anymore. We're going to basically transform everything into the S domain. Then you can see now, if I take a Laplace transform of this side here, okay, so we're going to have to make use of the property. So first there is, what's the Laplace transform of second order derivative of y function? So you're talking about the function of t, so this is basically dy over dt squared, okay? Yeah. So the first one here, the first one there is Laplace transform y double prime over 4y, okay, equal Laplace transform this one, I guess just indicated using capital F of s, okay? Yeah. And then here is basically Laplace transform of these two here. Okay. And the second one here, this is just Laplace transform y, so it's basically 4 capital Y of s. And the first one, that's where you need to make use of the property now. What property should I use? I'm going to use this property, right? So Laplace transform of this second order derivative, okay? Yeah, and which is this one, okay? Yeah. So then you put this one, basically put it down over here. This is s squared capital Y of s minus s y of 0 minus y prime of 0. Was that right? Yeah. Okay. So that's the property. Basically, use this one here. So don't forget the initial condition, though. Okay. Yeah. So in this, when we're solving it, we need to apply these initial conditions. Okay. So what's the initial condition here? Y of 0, 3. Y prime of 0, -1. So plug it into here. Okay. Then, and at the same time. Okay, at the same time, group the similar term. So you have this term has y of s. You have this term has y of s. So altogether, this is y of s, s squared plus 1. Okay. And the other two at here, right? One is s by 3. The other is 1. So then that's negative 3s. Plus 1 equal f of s. Okay, f of s. Okay, yeah. Okay, so remember the purpose, right? The objective is to solve this one. Basically, the objective is to what? To obtain what? To obtain this guy here. Okay, yeah. Now, what happens is after this bunch approach here, you single out, so you're going to try to single out this y of s, capital Y of s. So then you're going to take a inverse Laplace to get back this y of t. That's basically the idea here, right? Yeah. So then let's single out this capital Y of S here. So move this chunk to the right side and divide this S squared plus 1 by both sides. Yeah. 4, yes, that's right. Oh, no, sorry. Oh, this is 4, that's right. This is plus 1, right? Yeah. Is that right? That's plus 1? Yeah. So, yeah. So then let's move this term to the outside. Move this term to this 3s minus 1 plus f of s and divided by s squared plus 4. So that's y of s, right? That's y of s here. Okay. And I'm going to separate this term into two parts. One is this, and the other is this. Okay. Yeah. So then, up to here, then you should try to take inverse Laplace of this whole chunk, try to obtain this y of t now, right? Yeah. But let me give you an example here now. Okay. Let's say suppose we're gonna do this. Before we do that, let's do this. Okay, let's do this. Okay, I'll still keep this one in here. For this part here, okay, for this part here, I'm gonna break this part. Okay, break this part into two parts. So 3s over s squared plus 4. Okay. The other one is 1 over s squared plus 4. Is that good? Yeah. And then here is 1 over s squared plus 4 multiplied by f of s. Okay. So nothing really changed. Just to write it in a better way to look at it. Okay. All right. So then we're gonna take the inverse Laplace, right? Inverse Laplace. So taking inverse Laplace, okay, means we have to break this down to the simplest form. So now I can tell you now this is actually the simplest. You can't break it down to even simpler anymore. All right. So if I look at my table now, so let's take a look at what's the inverse Laplace for the first term, what's the inverse Laplace for the second one, what's the inverse Laplace for the third term. All right. Yeah. So do I have a similar Laplace transform in this table here? Which one is similar? This one here, right? Yeah. This is s over s squared plus omega squared. So omega should be, in this particular, omega is 2. So exactly. So the first one actually inverse is what? Cosine 2t. Okay, cosine 2t. And second one, this is 1 over s squared plus 4. Now let's go back here. Where do we have? We have omega over s squared plus omega squared, right? So, but this is not 1 in here. Okay. Now maybe I'll do this. I'll put a 2 at it here, but then I have to divide it by a 2 here, right? So now if I look at this chunk at it here, this is 2 over s squared, and this is 2 squared. So what's the inverse Laplace of this one? That's sine 2t, right? Sine 2t. So overall, this is 1 over 2 sine 2t. Okay. So we'll talk about this scale a little more later. Okay, but can you see this change it here? The simple change. Okay. Yeah. So all the changes for the purpose to use the table, right? Yeah. The last one. What's the Laplace transform of these two? F of t and what? What should I write here? Convolute, yes. Convolute to which one? Sine 2t. What's the 1/2? That's right. Yes. Okay. Why convolute? That's exactly the same. The first application that we just learned here. The multiplication of a 2s function. The inverse Laplace is a convolution, right? It's a convolution here. Okay. So Now you look at this one here. As a matter of fact, okay, let's relate to trying to relate to what we have learned so far here. Okay, now basically there are sort of two terms that are here, right? Two parts that are here. Second part is the convolution, and the third part is some kind of time function here. Okay. Now if I look at the way that it has been solved here, or you look at it back to think back of what we learned here. Now when we're learning the linear system. So we were talking about a linear system, basically when you have an impulse response, then when you give an impulse signal, you have the impulse response, and then when you give a different signal, then the new output will be just basically the new input convolute this impulse response, right? Yeah. So you look at this one here, that's actually what we're talking about there. Okay. So what's the impulse response of the system? Here. Okay. This is the impulse response. Okay. And the first portion in here, okay, the first portion in here, that's actually basically it's the homogeneous solution. This is basically the homogeneous part of the solution. And this is a homogeneous solution with the given initial conditions. Okay, with initial conditions. Okay. And this part here is the so-called non-homogeneous solution, or this you can call it basically the convolution with the impulse response. But when you do this part here, we're going to call in details here. When you have this part here, there's no initial conditions being considered here. So that initial condition purely showing up in this portion. As a matter of fact, if you look at the process here, where is that 3s plus 1 from? Initial condition, right? Yeah. If my initial condition is all 0, I won't have this part here, right? I won't have this part. It's just going to be this part here. Okay, yeah. So, but you look at this whole this example here. This is basically sort of showing you the general approach of solving second-order differential equation using an even higher order, okay, using Laplace transform, okay, Laplace transform. Is that clear? Yeah. Okay. So some of the detailed skills we're going to refurnish that later, but that's the overall picture. Okay. Now I'll give you a diagram. Okay. So now looking back at here, I'll give you a diagram as to what's the general approach of solving Laplace transform here. So the diagram is basically you starting with your ordinary differential equation. Okay, so here's ordinary differential equation. This is everything in time domain, right? Yeah. And then we take Laplace transform. Okay, take Laplace transform. So after you're taking Laplace transform, as shown in the previous example, and we change ourselves, okay, from time domain into S functions, right? Yeah. And what happens is, for this step here, we take Laplace transform and we try to obtain an expression for this capital Y of S. Okay? Yeah. So basically, obtain the S function for output. Okay? For example, Y of S at here. Okay? Yeah. So this is a case, this step here is a key step because you need to apply the initial condition. You need to apply the property properly so you can obtain the right Y of S, right? If you don't have the right Y of S, then all of this next flows won't make any sense. So then the next step, okay, is the objective to solve for Y of t. So the next step is you break down or decompose, basically decompose this Y of S, into the so-called simplest of terms. So simplest meaning the kind of format that you can find in the table that you have. That's the simplest. Okay. Yeah. And this step needs a little bit of skill here, so we're going to look at actually different kind of skills. Okay, in terms of how do we decompose this y of s into the simplest form. So sometimes it's very easy, sometimes you need a little bit refining there. Okay. So once you obtain the simplest form, okay, then you go to your table. Okay, go to use table to find. Okay, so use table. Okay, to find y of t. So that's the typical approach at here. So then in the end, you got your solution y of t at here. So Laplace transform solving differential equation has a huge advantage in terms of what? In terms basically, you see the whole general approach here. When you're not using this, when you're using the traditional approach, particularly for initial value problem, in the end, what do you have to do? You have to substitute the initial value back into the solution, then solve for those constants here, right? But when you're using Laplace transform, everything basically is done in one shot. So then you end up with the value of the constant you're looking for actually. Okay? Yeah. Alright, any questions? Okay? Yeah. Okay. So now let's take a look at a couple of the cases here. But before we do that, I think I want to talk about one simple concept here. Okay? Now, for typical y of s, if you look at this y of s right here, okay, so basically in the end, you try to obtain an s function for y of s, right? But this y of s will always taking in the form of these fractions, basically numerator over denominator here. Okay, so this y of s is going to be a numerator function of s over a denominator of function of s. And what we're going to need, the information out of here is, okay, one of the information that we're going to need is, when you set this d of s equal to 0, okay? Yeah. So basically, we're trying to solve for the s that satisfy this d of s equal to 0. Okay, so we're going to need that information. Okay, this s here, that the solution for s is called pose. Okay, so this is a new concept thing. It's called pose here. Okay, and when you set this n of s equal to 0, okay, the solution for the s at in this case is called zeros. Okay, it's called zeros. So those are kind of concept in control system in digital filter design. Okay, so pose and zeros, okay, like this. Yeah. Taking limit, you mean? Oh, true. Yeah, you cannot. Well, yeah. I mean, you cannot have this term 0 here, but if I single this ds out, right, I can set equal to 0 and solve for the s that satisfy ds equal to 0. Okay, so this is this has actually not much to do with now what happened to the fraction here. Just we're gonna just look at what s will give you a d of s equal to 0. Okay, that's sort of a standalone concept here. Okay, yeah, good. So we don't have much time, but I'll just start with this first case study here. Okay. Now all the cases I'm going to show is actually focused on this portion here. How do I decompose a y of s into a simplest format or item, simplest terms here? Okay. So the first kind of case is if y of s is taking a form like this. Okay, it's taking a form like that. So if you look at this form here, so what exactly does it mean? So look at this one here, right? So it's a numerator divided by the denominator, okay? And the denominator is a multiplication of many of these factors. And each one of the factor basically, okay, is the simplest format here. So it's s plus something here, right? Yeah. So technically, look, this is what I'm trying to talk to you about here. If I set this denominator to 0, right? So basically, what makes it 0? When s equal to negative p1, when s equal to negative p2, when s equal to negative pn, right? Yeah, that's what we call the s, the solution. Those s are poles here, right? Poles. So this is the case where we call when you have a simple pose. Okay, this is a simple pose here. All of the poses here are basically, we consider them as reals here. Okay, so they're real numbers. Okay, they're real numbers. And that's the case. How do we decompose this into the simplest format? So the way to decompose, I'm not going to talk about these, but you will decompose like this. So K1 over SP plus 1, K2 over this, and plus Kn over this. Okay, so that's how you decompose when you have such case. And of course, the question is what will be the K1, K2, Kn, right? So that I'll talk about next lecture. Okay. Any questions? Yeah. Okay. So I'm going to give out assignment number 9 today, but you have a 25th, I think, for the due date. Assignment number 10 will be taking home exam, taking home assignments. So no need to submit, but you still need to do it though. Okay, so that's basically what's going to happen.